Hey guys, so I want to do a quick generalization of what you've learned with deriving Euler-Lagrange equations for one function and having the integrand of s be dependent on that one function and its first derivative to multiple functions. Cool. So what the heck do I actually mean by that? So what we've been studying so far is you're given an s, and s is called a functional. And the reason it's called a functional is it depends on some function that you're integrating over. What I mean by that is the following. We take the argument of the function x, and we write an expression, which is the integrand L, which can depend on x independently of a function y and its first derivative. So that's what you've known so far, right? And so there's a reason that I'm not closing the parenthesis over here. What if we have multiple y's? So y1, y prime 1, y2, y2 prime, all the way to yn, yn prime, right? So what I'm saying here is, what if x depends on multiple functions that we need to plug in, and we want to extremize s? We want to figure out when is it that s is at a minimum, maximum, or saddle point. So this is going to be very similar to what you've done before, except for one catch. You can't vary the same, you can't vary every function that shows up in this integrand by the same amount, namely by the same eta that's been showing up in all of our problems. Why is that, you might ask? Well, the reason why is exactly the reason that you can't do that in multivariable calculus. So in multivariable calculus, you have some function that depends on x, y, z, w, whatever, you name it. And if you take partial derivatives, you can take partial derivatives in different directions in that space. You're doing the same thing here. You're basically saying, I want to take a derivative of s in this function space, so this space of y1, y2, all the way to yn. And you could take that in different directions in this function space. So we're going to introduce something that's universal to all these functions, namely alpha, which has been showing up before. We're just going to say shows up everywhere here. That's going to control whether or not, how much the functions that we vary the yk by, how much they're actually varied. So we're going to vary each yk by alpha, which is common to all of them, times eta kx, which is a function that is specific to the variation we're doing of the kth y. Cool. So this is going to be the same work that we had before. So ds, d alpha is an integral over x. One point that I forgot to make is that the etas are going to just vanish at the endpoints. This is something that's come up in the other videos. So we can write this as a partial derivative with respect to alpha of the integrand. Now, we're going to skip a little bit of work here. So we've already seen how you actually do integration by parts to get it so that the eta, in the case of one function, shows up in front of an entire expression. The same exact work applies here, except we need to repeat it n different times. So that means that we're going to have eta 1, which we can apply calculus of variation, so its first derivative vanishes, gets put onto the other stuff in the expression. This is going to multiply dl dy1 minus d dx dl dy1 prime. The same thing is going to happen for eta 2. Eta 2 is going to multiply dl dy2 minus d dx dl dy2 prime. And we just repeat this n times until we get to eta n x is multiplying the same stuff, just with, yn instead of y2 or y1. Cool. So here's the trick. All these eta 1, eta 2, eta 3, eta 4, all the way up to eta n, those are arbitrary functions. They're arbitrary functions that, don't depend on each other. So the stuff in parentheses, if this is going to be set equal to 0, the stuff in parentheses in front of each of them independently needs to be equal to 0. What that means is that for each function yk, we'll find that we'll find that dl dyk minus d dx dl dyk prime is equal to 0 for each k. So what's kind of cool about this is that you actually end up with n different expressions for the n different y's that show up. Just a point here, why would we actually care about a generalization where we have n different functions showing up? Well, here's what you're going to see as we move into the next week of the course. These y's that are showing up, they represent coordinates in a classical system. Those coordinates depend on time. If you have multiple coordinates, meaning maybe you have multiple balls that you're tracking in a system, or you are in a multi-dimensional system, so a ball in 2 dimensions, there's going to be multiple coordinates that you actually have to take into account, which change, what their value is over time. That's why we end up with multiple functions that are going to be functions with respect to time that we want classical equations of motion for, which are represented in this new formalism of calculus of variations that you're learning. Cool. So I think we have beaten the horse dead of all the different variations that we can do on calculus of variations. And so, like I said, if you guys have any questions, send me to the Discord channel. We'll go over, whatever you like. I can make additional videos. But until then, hope you have a good rest of your week.